Hi everyone, thanks for having me here. Thanks to the GoEd team for inviting me to speak about meta-analyses. I have a lot to say. I'm not going to get to say it all in this next 25 minutes. So I welcome those of you that are interested to harass me over lunch or get in contact with me. So I'm going to start off by talking about the trend of meta-analyses. People have been talking about how this approach has been increasing, used increasingly. I'm going to talk about what it is, why we do them, how we conduct them, and then go over some of the pitfalls associated with this approach and make just a brief conclusion about meta-analyses. So the rise of meta-analysis. I came across this figure as I was going through the literature preparing for this talk, and so this paper was written in 1997, and they were like, wow, meta-analysis is becoming really popular, we need some guidelines, we have this linear increase of publications that are using meta-analyses. And I thought, whoa, well, I wonder what's happened over the past 2 decades, okay? So I went ahead and did a PubMed search of meta-analysis. And it seems that we've now entered an exponential growth phase of meta-analysis. They're multiplying like bacteria. And I thought, this is really interesting. And then you know, the critic in me started thinking, oh, well, there's a lot more journals nowadays. There's just a lot more publications. So what if I look up something that's probably been studied forever? What if I look up stroke? Okay, there's also a pretty big increase in stroke, although not quite that exponential growth. I thought, well, what if I look up other types of analyses? Because statistics has become, over the past couple of decades, a really fundamental piece of health research. It's now required by a lot of funding agencies to have a statistician on your grant. So I thought I'd look up some common analyses done in health research called logistic regression. And that, since 1990, has far exceeded meta-analysis. So we've got this just rise in analysis happening. So I thought, well, okay, but there must be something to analyze then, right? So what if I look up randomized control trials? So sure enough, there's a ton of more randomized control trials. I'm not exactly sure what's happening there in 2014, 2015. Maybe it's reflecting the funding environment, but I think it's probably just an artifact of the database. Those publications haven't been listed in the database yet. But there's just this rise of things to be analyzed. There's this rise of evidence. There's tons and tons of studies that we need to wade through. And that kind of makes sense then why we're seeing more systematic reviews and meta-analyses, because we need to synthesize that evidence, okay? So what is a meta-analysis? Okay, get ready. This is an equation coming up. Okay, you invited a statistician. Here we go. And meta-analysis is a weighted average, okay? Simple as that. You're taking the effect sizes from different trials and weighting them and averaging them to get one estimate, okay? And a confidence interval. You never just report the estimate. There should be a confidence interval associated with it. All right, so that's meta-analyses. There's different ways of doing this, sophisticated ways of doing this, but on a basic level, this is what a meta-analysis is. So why would we do this? Well, there's a lot of reasons. First of all, a meta-analysis provides reliable information about anticipated effect sizes. So it helps us plan that next trial, that epidemiological trial. How many people do we need to recruit? It helps us identify the effectiveness domain. So how robust is the treatment across various types of patients, diseases, and outcome criteria? It promotes transparent reviews and provides reproducible estimates. So before meta-analyses became popular, everything was very qualitative, and it's very difficult to reproduce qualitative work. So a meta-analysis gives us something that is really reproducible. Meta-analyses can be very helpful for evaluating product risk because a lot of these side effects can be very rare. So you need big sample sizes in order to identify adverse events. And this is how the FDA uses meta-analyses. Finally, the scientific approach requires more than one study to make a definitive conclusion, okay? And it helps achieve the maximum benefit of prior research. Okay, and so this is the synthesis of prior research is why meta-analyses, which is on the top there within systematic reviews, why these are placed at the top of this evidence-based medicine pyramid oftentimes. Okay, so at the bottom you have expert opinion, at the top you have systematic reviews. This particular pyramid was published by the American Diabetes Association. And different groups place different weight on meta-analyses and systematic reviews. The International Agency on Cancer Research that recently made the very controversial statement, classification of processed and red meat as possibly carcinogenic and carcinogenic, used a meta-analysis and systematic review. Okay, so these can have huge policy implications. Okay, so now, how do we conduct a meta-analysis? All right, I'm going to be taking you through the to-dos and not to-dos of meta-analysis. Probably most of you are not going to conduct a meta-analysis yourself, but these will help you evaluate how much stock you put into a particular meta-analysis. And to do this, we're going to be using a case study. You've seen this one already in a previous presentation. This is a study by Rizos, looking at the association between omega-3 fatty acids and risk of major cardiovascular events. Okay, so things to do in meta-analysis. First, write up a review protocol, okay? And register that protocol. So it's out there. Before you collect your first piece of data from the literature, you want to have that protocol and you want to stick to that protocol. If there's any changes to that protocol, they should be documented and the reasons should be documented, all right? So that prevents us from just kind of willy-nilly saying we're going to include this paper and we're not going to include that paper. We've got a protocol, we're following it. And Rizos did that. Secondly, we want to see that trial selection and data extraction were done in duplicate and independently by 2 or more reviewers. You do this when you're extracting data from medical records. You should do this when you're extracting data from published articles. Okay, so let's look at our case study. Here we go. Data extraction was performed independently by 2 investigators and discrepancies were resolved by another. Okay, so far so good. Next, we want to see that the authors assessed the methodological quality of the trials included in the systematic review. This is because there are factors that have been demonstrated to be associated with biased results. Not all randomized control trials are the same, are equal. Okay, these factors are listed here. There's 4 of them. Generation of the allocation, randomized allocation sequences, concealment of those randomization sequences, blind assessment of the event. In things like mortality, probably doesn't matter. They're either dead or alive. But if you've got a radiologist that is looking at images, you want to make sure that radiologist doesn't know who got what treatment. And intent to treat analysis. This is analysis that takes into account that some people drop out of studies, okay? And you want to make sure that that's not causing bias in your results. So Rizos did evaluate each study on these 4 criteria, and it's listed in the supplemental material of that publication. And some of these large trials actually fell short on some of these elements that can cause biased results. Next. Okay, next we want to, come on, there we go. We want to estimate statistical heterogeneity. So what is that? It simply means, does the treatment effect vary between the trials? So we want to see that they've looked at it. And you're going to see one of two, maybe both of these statistics reported, I squared and tau squared. I'm not going to go over what they mean, but the lower those numbers are, the less heterogeneity there is between trials. Okay, so the more similar the results probably are. Okay, the higher the number, the more heterogeneity. Okay, then we want to investigate possible sources of heterogeneity. Why are these trials different? Why are we getting different effect estimates? And can that heterogeneity be described by attributes of the trials, like subpopulations, co-interventions? Maybe some trials had folks on statins, other trials didn't, and the quality of the studies. So you did that quality assessment. We're not throwing out any of those studies, but we'll do a sub-analysis of the, say, the low quality ones, and these are the higher quality ones, and we'll present all of that information. Okay, and we want to see that they have made a plot like this. I'd love to explain this to you. If you want to know how to interpret this, I'll tell you, but I'm not going to do it right now. But this helps, it's called a funnel plot, and it helps you assess publication bias. Not every trial is published, and the trials that are published are more likely to have positive effects. You absolutely need to understand this when you're going through the literature. There's a lot of trials that are null or maybe even negative that have not made it into publication. And this plot helps you assess if there's publication bias. Next, we want to see that the authors have used a forest plot to display results. So this is one of the forest plots from Rizos. These are great. They show the results of all of the trials that are included. You have the confidence intervals there. You have the estimates in the black boxes. The size of the black boxes correspond to the weight that trial was given in the meta-analysis, okay? So the larger trials are given more weight. The smaller trials with large confidence intervals are given less weight. So let's take a closer look at this. We notice in this forest plot, there's kind of three groupings of papers, and they're labeled mixed prevention, secondary prevention, and ICD. Okay, this is part of that investigating this possible sources of heterogeneity, right? So mixed prevention settings versus secondary. So secondary means everybody had already had an event, and we're trying to prevent the next event. Okay, and then ICD is some of these folks, these trials were on folks with implantable devices. Okay, so the authors were looking at possible sources of differences in these trials, right? So this is an important thing that you want to see. Next, you want the authors to examine the effect estimate and its 95% confidence interval. Those should always, always, always be included. Okay, that 95% confidence interval should be included. And the manuscript should be written up using the recommendations of the PRISMA statements or MOOSE if it's observational, if you're doing a meta-analysis on observational studies. So there's guidelines for how these should be conveyed to the public. Okay, now, what not to do. And these will raise red flags if you're reading a meta-analysis. These should raise red flags. Quality assessment tools to derive quality scores should not be used, and the trials should absolutely not be weighted by those scores. This was a very popular recommendation about 10 years ago, and it's still being done, and it should not be. These quality assessment tools are not based on theory. They can result in biased estimates. Depending on which one you use, you can have positive results, you can have negative results. It's all over the place. So the theory-based methodology is to weight only on the sample size. Well, technically the variance, but the variance depends on the sample size. Okay, do not use quality assessment tools. We don't want folks summing up the individuals from trials as if they all belong to one big trial and analyzing it that way. That's wrong. okay? That meta-analysis, you shouldn't put much stock in that meta-analysis. You don't want folks using the tests of heterogeneity, so figuring out how different the trials are, to decide whether they're doing a fixed effect or a random effect model. Okay, what's the difference between these two things? One is the fixed effect assumes that there's one common effect across all subpopulations, across all clinical settings, one common effect, and the trials are just imperfectly measuring that one effect. Random effect means there's actually different effects in different settings in different people, okay? This is a belief. This does not depend on the heterogeneity that's measured, okay? It's what you believe is true based on the science. You don't want to see that associations between treatment effects and patient characteristics that have been aggregated at the trial level are being regressed upon. They're not looking for associations, like with mean age of the trial or percent of females. This could result in what's called an ecological fallacy, something that's true at the top, but not true if you have individual patient data. If you have individual patient data, you can do this. Otherwise, no way. Finally, we do not want to describe the results as not statistically significant or non-significant. Okay? Let me illustrate why. Let's take a look at this is the summary figure from Rizos. You've seen this already. We've got the different outcomes that they're looking at. The first one is all-cause mortality. We see that that confidence interval is overlapping 1, which is a equivalent effect. We see that cardiac death falls below 1. The confidence interval falls below 1. And sudden death is a wider confidence interval that overlaps 1. And then there's others. So it's really confusing when you have this plot, but the authors conclude this did not show a statistically significant association. We have the relative risk, we have the 95% confidence interval, we have a p-value of 0.01, and we have very low heterogeneity between the trials. So this is really confusing, right? And if you read through the methodology, you see that they've done a p-value adjustment because they were testing multiple outcomes. But in the world of statisticians, we're really moving away from using p-value cutoffs and making these hard and fast decisions based on p-values because they're very arbitrary. And if you do something like a p-value adjustment, you have somebody like Aldo giving you a call and saying, why did you use this adjustment when you could have used this other adjustment? It's a really subjective thing. Statistics is not mathematics. It's an imperfect, well, it's a very subjective art, actually, if I can be so bold. And meta-analyses, the interpretation of meta-analyses need to be nuanced, okay? It should not be black and white, not statistically significant, or yes, it is statistically significant. It needs to be interpreted in terms of evidence. So for cardiac death, I would say there is evidence of a small effect of omega-3 fatty acids on prevention of cardiac death. For sudden death, I would say there's not enough evidence to conclude it's protective, but this is the beauty of meta-analyses. It's identifying that there's not enough evidence. Okay, this is an area where we need more studies. If you look at that, there's only 7 studies that were included in this meta-analyses. Okay, so as a statistician, this is how I would have encouraged the authors to interpret the results. Rely less on a strict p-value cutoff and talk more about the strength of the evidence. Okay, so we have good evidence of a small effect of omega-3 fatty acids on cardiac death. Now, small effect, the relative risk is 0.91, which in the previous, if you're an economist, that translates to millions of dollars, possibly billions, so over the entire world. But in terms of things that we see, effect sizes we see, it's a small effect. Okay, so meta-analysis, meta-analysis. I stole this slide title from Sam Shapiro, who is writing a commentary about meta-analyses in the Journal of Epidemiology. And I thought it was great for talking about the pitfalls of meta-analysis. So first of all, while in principle meta-analyses are very appealing and based on solid theory, the practice is messy and results are ambiguous. So we have different methods resulting in different conclusions. We have inherent heterogeneity because studies are different. And this really is a problem for relating to clinical practice because you're taking this average. You're taking an average over different countries and totally different clinical settings and different ways of giving people omega-3 fatty acids and different dosing. And really, if you average that, what is that population? What does an average population look like? And why do I care about some fake average population? Okay, so this is a real difficulty with creating that one effect estimate. The results are only as good as the studies included. Like I said, some of these large trials are actually lacking in some of the methodology that they used. Also, for omega-3 supplementation, one argument is that you should be looking at not just the intake, but you should actually be looking at the omega-3 status circulating in their blood as the exposure. There's bias in publication, and there's always this issue of you can bring a lot of studies together and get really significant results and identify a very, very tiny effect that really doesn't matter. So that balance is difficult. Next, experts don't agree on approaches. How do we assess publication bias? There's different statistical pooling techniques that can be used. How do we handle unpublished literature? Okay, these are all things that are still in development in meta-analyses, and the methods are still very much in debate. So the other thing is that meta-analyses suffer from the same drawbacks as observational studies, so confounding, bias. If you imagine a randomized control trial is randomizing treatments to subjects, but the trials themselves are not being randomized to countries or principal investigators. Okay, it's the people that want to study it that are studying it and have the money to study it. So although they follow from sound principles, they may not be seen as evidence-based. And the Journal of the American Medical Association, JAMA, will not let you make causal conclusions from meta-analyses. They do not want to see any causal verbiage in your paper that you submit if it's a meta-analysis. So it brings into question whether systematic reviews and meta-analyses should really be at the top of that evidence-based pyramid. But there are things that are there to help us, like the Cochrane collaboration. They have been identifying as many control trials as possible in any language. Language bias is a huge issue when you're doing systematic reviews. And they've got these all listed in the central register called Central. Any meta-analysis that's being done should be using this database. Okay, every single meta-analysis should be using this database. But still, this is imperfect because we know there's publication bias. So what we actually want to look at trials rather than publications. And this is why. So this is an example of two different treatments for ovarian cancer. In the published literature, there's a highly statistically significant effect of a combination chemotherapy, okay, over the standard. But then when you go, and fortunately, there is a central research data bank where every cancer trial is registered. You can go to that data bank. It may take more work because you might need to contact the investigator directly to get the results of that trial if it's not published. But if you do that, it can bring that estimate to a whole different place, okay? So you really, really, really need to be aware of publication bias. And what we really want is some registered trials. Really quickly, about meta-analysis of observational studies, this requires even more scrutiny because essentially you're doing an observational study of observational studies. Some people say you shouldn't even do a meta-analysis on observational studies. I wouldn't take such a hard stance, but they do need to be scrutinized quite carefully. Okay, so here's my brief conclusion. The bottom line, how meta-analyses are received varies, but the most highly regarded groups do not consider it at the top of the pyramid yet. Okay. Data sharing initiatives are going to allow meta-analyses using individual patient data, okay, which is a gold standard approach. If you can get the information from every patient, from every trial, that's going to give you much more leverage. And so I encourage you, if you haven't already been supporting initiatives for sharing data from clinical trials and observational studies, that should be high on the list because it's going to help give more, better, unbiased estimates and allow for a richer interpretation of the effects. Finally, if you're considering a meta-analysis, realize they require both clinical and technical, read statistician, expertise and take considerable planning, time, and effort. This is not something that a graduate student should just be shoved off doing, before they do their real work for their dissertation, which is often what happens. There's a lot of crap meta-analyses out there. It takes a lot of planning and a lot of effort to do a good meta-analysis. Okay? So with that, I'll conclude. Thank you very much.